All right, so we'll start with number 6 here on the static electricity assignment. What are the magnitude and direction of the electric field 26.7 centimeters directly above an isolated 27.2 times 10 to the minus 6 Coulomb charge? All right, so first of all, any forces here, do we need to do, in other words, do we need to do a force diagram as part of our Y? No forces here. So, number 6. The first thing I would show is that I understand that all charges create electric fields around themselves. And let's see, did they give us a positive or negative charge here? Magnitude direction of the, I've got a positive charge, so I'm going to say that electric fields point away from positive charges and get weaker the further I move away. So I'm showing that I understand that about electric fields and how they're created in my Y. The big one, and then also getting that idea of the specifics of them point away and they get weaker the further I move away. So now, any question on that before we jump into the how? No? Good. Alrighty. So grabbing our equation sheet, I'm going to turn to the second page of it. And I'm looking at my E field area of the equation sheet, and I've got 2 equations in it. The left-hand one, which describes how the relationship between an E field, an electric field, and the charge that creates it. And then the right-hand one, which describes the relationship between the electric field and a charge that's in that field. So remember, that's the big difference between these two. Left-hand, electric field, and the charge that creates the electric field. And the right-hand one, the electric field, and a charge that experiences that electric field. So, is this problem about an electric field and the charge that creates it, or an electric field and a charge that experiences it? This one's about creating it. So that's why, equation-wise, I'm going to use the electric field equals KQ over R squared as my equation. So, electric field strength E is KQ, the charge that creates it, over R squared, how far I am from that charge. Okay? So, let's see. Things that I know. I know K from my equation sheet, the part that's on the back of the rubric. I have K down here, Coulomb's constant, which is the description of how these forces interact with the universe. 8.988 times 10 to the 9th Newton meter squared per Coulomb squared. That's what tells me I have to have all my distances in meters, all my charges in coulombs. All right, because if I'm using that value for K, I've got to make it align unit-wise with my other things. And so I'm told that I have a distance of 26.7 centimeters. Better convert that to meters. And it has a charge of 27.2 times 10 to the minus 6 coulombs. So good, I'm already in coulombs there. So now it's really, it's plugging in. So it's K, which is, I just said, 8.988 times 10 to the 9th Newton meter squared per coulomb squared times my charge, 27.2 times 10 to the minus 6 coulombs over my distance away, 26.7 centimeters, which is 0.267 meters squared. And I will find my electric field strength, and it will be in newtons per coulomb due to using the correct values. Let me know if you need help individually on that one. All right, we're going to move on to number 2, where it says how many electrons make a charge of, for B, negative 10.0 microcoulombs. So there's one really crucial understanding here to make sure you have in your Y in this type of problem, is that an electron has one quanta of negative charge. So remember that charge, isolated charge, only comes in these little packets of quantas. That should be an A, quanta. So that's really all you need for your Y there on this one. And then we jump to our equation sheet. And we look in our charges section of our equation sheet and see that the charge on something, Q, is equal to N times the how many quantas are on it. So that's our equation we're going to use, that Q equals NE. We go down and flip over to our formula of facts and constants here, our constants, and we look down the bottom where we have the value of quanta in coulombs, which is 1.602 times 10 to the minus 19th coulombs in each quanta of charge. So now we just do a little substitution. Let's see, mine was negative 10.0 times 10 to the minus 6 coulombs. Converting that microcoulombs to coulombs equals N times 1 negative, because it's electron carries negative quanta, negative 1.602 times 10 to the minus 19 coulombs. And I solve for the number of electrons, which is the N. And that does it. I got that from my problem. And using the metric prefix for micro. All right, so we might as well finish this assignment off with number 3. Calculate the net charge on a substance containing a combination of this many protons and this many electrons. All right, so what you would, major points you would need in your Y. Electrons have one quanta of negative charge. Protons have, how many quantas does a proton have? Right, one. Quanta of positive charge. And I'd also hope that you would express that the net charge is due to the imbalance of positive and negative charges. So, as we discussed, like on the first day, the things are charged because of the imbalance of the charges, not because they have charges. So, looking at our values here, I'm looking for the difference between the protons and the electrons, and so I have more protons than I have electrons, so a little bit of a subtraction there. I take 4.9 times 10 to the 13th protons, and I subtract from it 4.1 times 10 to the 13 electrons. I get 0.8, that's an 8, terrible 8, 0.8 times 10 to the 13th, and they're going to be protons that I have extra. So I'm looking for my net charge, Q. I know from my equation sheet that's N times how many quantas I have. As stated in my Y, each proton has one quanta of a positive type. So my net charge would be how many I have, 0.8 times 10 to the 13th, times the charge on each one, which I get from my equation sheet, 1.602, times 10 to the minus 19 coulombs. And it's positive since it's protons and they carry a positive quantum. And then I just multiply those correctly.